In this video, the learner will write a vector in component form, calculate the magnitude of a vector, and perform operations with vectors. Here we have a vector in what's called standard position. A vector is said to be in standard position when the initial point, the tail, is located at the origin. So for this vector, P, we have the initial point at the origin and the ending point at x, y. We want to write the component form of this vector. The component form of a vector describes the horizontal and vertical change from the initial point to the terminal point. We can look at that horizontal change, that change in x, which will be that x component of our component form. We can look at the vertical change, which will be the y value of our component form. Once we look at component form, we have the change in x, comma change in y. It looks very similar to just a point on the coordinate plane. Notice how the brackets are different though. This indicates that our vector is in component form, which tells us our change in x is our x component, how far we moved horizontally, and in what direction, and the y component, which tells us how far we moved vertically and in what direction. So let's take a look at writing the component form. First, we have the component form of CD. Well, just looking at the graph, we know our initial point here is at 0, -1, and our terminal point is at 4, 1. From our initial point, we're moving to the right 4, and we're moving up 2. So our change in x is a positive 4, and our change in y's is a positive 2. Now we can find this algebraically using the component form formula, where it's x2 minus x1 and y2 minus y1. In this case, x2 and y2 are the terminal points coordinates. x1 and y1 are the initial points coordinates. You'll see why we have to do that shortly. So when we plug in the terminal point x minus the initial point x, we get 4 minus 0. Terminal y is 1 minus the initial y, which was -1. 4 minus 0 gives a positive 4. 1 minus -1 gives us a positive 2, which is what we found graphically. So the component form of vector CD is positive 4, positive 2. Now, if we were to have written this the other way around, if it would have been 0 minus 4, that would have given us -4. If we would have written -1 minus 1, that would have given us -2. So that would have given us an incorrect component form because positive 4 and positive 2 also implies those positive directions of right 4 and up 2. Now let's take a look at PQ. Using the formula, we'll have -3 minus a -1 because our terminal point is Q and our initial point is P. And we'll have -1 minus 3. -3 minus -1 gives me a -2. -1 minus 3 is a -4. Now let's verify this graphically. If we started our initial point P, we would move down 4 and then left 2. Left 2 is a negative direction in the amount of 2. So our x component was -2. We moved down 4, which means we moved 4 units in a negative direction. So our y component was -4. Now let's look at this the other way around. What if we're given the component form and we're asked to sketch a vector with that component form? We could, of course, put that vector in standard position, which would be at 0, 0. But we really could choose any point we wanted to as long as it had this x component and this y component. Remember, the x component is the change in x values, so that's my horizontal change, and the y component is my vertical change. Therefore, an x component of positive 3 means we'll be moving right 3, and a y component of negative 7 means we'll be moving down 7. So as long as my vector is moving to the right 3 and down 7, we know we have the correct vector. So for example, this vector. My initial point is at negative 4, positive 5. My terminal point is at negative 1, negative 2. If I were to find the component form of this vector, I'm moving to the right 3 and down 7, which matches the component form we were given. I could, of course, move this vector anywhere I wanted to. I could put that vector in standard position with the initial point at 0, 0, or move it anywhere across the plane and still have the same component form. Let's take a look at another vector. This one almost looks equivalent to this vector. Notice though that my initial point is here and my terminal point is here. My initial point is at positive 7, negative 7, and my terminal point is at 4, 0. From the initial point, I'm moving left 3 and up 7, which is not the same as our given component form. For part B, I have the component form negative 8, positive 4, which means I will be moving to the left 8 and up 4. So I need to find a vector that has an initial point where I'll be moving left 8 and up 4. So this vector starts at positive 8, negative 6, and ends at 0, negative 2. Again, I can move this anywhere I want to. I could put it in standard position. Anywhere on the plane, this vector will have the same component form. Now let's take a look at equivalent vectors. When are vectors congruent or equivalent? Well, equivalent vectors have the same magnitude and direction. So let's take a look at this vector here. The component form of this vector would be positive 8, positive 4, moving to the right 8 and up 4. If we look at another vector, I am moving in the same direction and I have the same component form. Therefore, these two vectors are equivalent. I could easily find the magnitude by using Pythagorean theorem, and we'll do that in just a little bit. So these will also have the same magnitude. And because they have the same component form, they have the same direction. Let's take a look at this vector. Now I'm moving down 4 and left 8. Therefore, my component form is negative 8, negative 4. That means this vector has a different direction than these two vectors. My initial point is here, and I'm moving in a different direction. These are actually what are called opposite vectors. They will have the same magnitude, but opposite direction. Now we're going to find the magnitude of a vector. Remember, the magnitude is the length of the vector from its initial point to its terminal point. So we're going to have vector AB. We would notate the magnitude with using this notation here. It looks like absolute value bars, but it is notating the length of that vector. So let's find the magnitude of this vector. Well, we notice here that we're starting at R and moving towards S. So we're moving right 2 and up 5. Notice that this creates a right triangle. Therefore, we can use Pythagorean theorem to find the length of that vector. So we would notate the magnitude of RS in this way. You might also see the notation with double bars to differentiate it between absolute value. And so now we're going to find the length of that vector, or the magnitude of the vector, using Pythagorean theorem. So we have the square root of 2 squared plus 5 squared, which gives us 4 plus 25, which gives me the square root of 29. So the magnitude is the square root of 29. Here we have vector jk. If we take a look at where it's moving and creating that right triangle, we're going to be moving down 3 and to the left 6. Again, because we're using this right triangle, we can use Pythagorean theorem. So we're going to be finding the magnitude of jk using Pythagorean theorem. Notice here, once we plug in both -3 and -6, we're going to be squaring those. So it doesn't matter that we're using negatives. We're really not using those to represent length. We're trying to represent those vectors here for the horizontal and vertical components. So -3 squared is a positive 9. -6 squared is a positive 36. So we have 9 plus 36, which gives us the square root of 45, which simplifies to 3 root 5. So the magnitude of vector jk is 3 root 5. Notice each time what we're really using is the change in x's and the change in y's. The change in x and the change in y is what was plugged in to Pythagorean theorem. Therefore, we really can just use the component form to find the magnitude. So find the magnitude of the vector when given its component form of +6, -4. Well, we could just plug in +6 and -4 to Pythagorean theorem. We'll have the square root of 6 squared plus -4 squared. 6 squared is 36, -4 squared is +16. Add those together, we get the square root of 52, which simplifies to 2 root 13. Now we're going to take a look at finding the direction of the vector. Remember, the direction of a vector can be expressed as the angle with the horizontal or using cardinal directions. We're not going to be using cardinal directions on the coordinate plane, so we're only going to be looking at the angle with the horizontal. We're going to be using the same vector that we looked at previously, +6, -4. In order to find the angle with the horizontal, let's first sketch the vector in standard position. Standard position, remember, is where the initial point is at 0, 0, and then using the component form, we can construct that vector with a component form of +6 and -4. Now we're going to use right triangle trigonometry to solve for that angle with the horizontal. We notice here that theta is this angle inside that right triangle. So we can use opposite and adjacent to solve for this angle. So we would have tan theta equals 4/6. To solve, we would need to use the inverse tan. So the inverse tangent of 4/6 gives us an angle of approximately 33.7 degrees. Now initially we didn't use cardinal directions, but what if I asked you to write this as a navigational bearing? Those come from our north-south lines, and then the angle comes from there. We know that theta and this angle from south are complementary to one another. Therefore, this angle is 56.3 degrees. So I could express this angle as south 56.3 degrees east, because I'm moving east from south. Now we're going to take a look at finding the magnitude and direction of vector r with the component form -4, -5. So we're going to look at that graph in standard position. We are moving -4 and -5. That gives us our right triangle to be able to find the magnitude and the direction. So we used Pythagorean theorem, but we could also use distance formula between 0, 0 and -4, -5. So here's our distance formula between 0, 0 and -4, -5. And we get the square root of 41. Now to find the direction from the horizontal, and remember in math and physics we always look at our angle from the horizontal. We're going to use trig to find the direction. Well, we're going to be solving for this angle here inside that right triangle. So we graphed vector r, its horizontal and vertical components, and now we're going to use opposite and adjacent to find that angle theta. So we're going to be using tangent equals opposite over adjacent. So tan theta equals 5/4. We use the inverse tan of 5/4 to find the angle, to solve for the angle. So that angle is approximately 51.3 degrees. But because the direction of r is the angle from the positive x-axis, we have 180 plus 51.3 degrees, or 231.3 degrees. If we wanted to write this as a navigational bearing, we would look at that south line and we would need that angle from south. Well, if this angle theta is 51.3 degrees, we would subtract that from 90 and get 38.7 degrees. We would be moving to the left, which in our cardinal directions would be west. So this would be 38.7 degrees west of south, or south 38.7 degrees west. Next, we're going to take a look at operations with vectors. We have some basic properties of vector addition, subtraction, and scalar multiplication. If we are adding two vectors together, we're really just adding the x components and y components together. So AB plus CD is A plus C and B plus D. The same with subtraction. If we're subtracting two vectors, we're really just subtracting the components. If we're multiplying by a scalar quantity, we're just going to distribute that scalar to both the x and y components. So we're going to take a look at these operations with r, s, and t. So we're going to have vector r plus vector t. We're going to solve algebraically first. So vector r plus vector t is going to be 3, 4 plus 1, -2. So we'll really just be adding the components, 3 plus 1, 4 plus -2, which gives us +4, +2. Now we're going to take a look at what that looks like on the graph. So if we were to graph vector t from 0, 0 to +1, -2, so we're putting all of these in standard position. Vector r would be +3, +4. If we were to look at the resultant vector of those, the vector r plus t, we notice that it's graphed at +4, +2. Notice that we create this little parallelogram here. That's not on accident. When you get to physics, you'll take a look at resultant vectors and what's called the parallelogram method of finding resultants. Okay, next let's take a look at some more examples using r, s, and t. So solving algebraically, vector s minus vector r will have vector s plus the negative of vector r. So we'll have 5, -1 plus the negative of vector r, which will be a -3, -4. So we have 5 plus -3, -1 plus -4, which gives us 2, -5. If we check that graphically, we have negative r. The original r is positive 3, positive 4. So that becomes negative 3, negative 4. We have s at positive 5, negative 1. If we form that parallelogram, we get that resultant at positive 2, negative 5. Notice those parallelograms come together at that terminal point for that resultant vector. Okay? For 2t minus s, we have 2 times vector t plus negative s. So we need to multiply that scalar first and then add that other vector. So when we distribute that 2, we get 2, negative 4 plus negative 5, 1. And when we combine those components together, we get negative 3, negative 3. Again, we can sketch that resultant. When we have negative s, we get negative 5, positive 1. 2 times t gives us our positive 2, negative 4. Again, drawing those other vectors, we get this resultant vector of negative 3, negative 3.